Okay. Today we're going to start talking about, we're going to start actually delving into the hardware model that we presented to you in the first class. So we're going to discuss modulation, and we're going to discuss detection. We're going to use some of the concepts that we talked about in the, when we reviewed random processes. So let's remember the hardware model. We had at the transmitter, remember that we had the data source fed into a modulator. That modulator's job was to transform the binary bits from the data source into some discrete time functions that could be transformed into something transmitted over the channel. So after the modulator, we go to digital to analog, and then medium access, physical air access. Okay, so right now we're going to talk about the modulator. What goes on in the modulator? This basically transforms a sequence of bits into a discrete time, a discrete time function. So we have a sequence BK, or excuse me, I'm going to use the notation J for this. BJ. So BJ is a sequence of bits. So for example, this could be 0, 1, 1, 0, 1, and so on. This is from the data source, and our job is to basically transform that into something that can be transmitted. So the approach. Is we're going to define two discrete time functions, S0 and S1. And basically we're going to replace 0, S0, replace 1 with S1. In other words, wherever I see a 0, I'm just going to drop in S0. Whenever I see a 1, I'm going to drop in S1. So obviously these functions can be overlapping. So that means a couple of things. Functions 0 S1 are non-overlapping. Can't overlap. For now, they can't overlap. We might talk later about cases where they do overlap. Since they can't overlap, that implies that they have to be limited in time. Define T sub B as the duration of a bit. So in other words, T sub b is the length of time during which S0 or S1 can be non-zero. Remember, these are discrete time functions, so I'm going to define T sub s as the sample time. In other words, time between discrete instants. Or in other words, it's basically the time between k and k plus 1. So that means I can get the number of samples that are allowed to be non-zero. And how would I do that? So let's let n sub b is equal to the duration of a bit measured in samples. So what would that be equal to? So TB is bits per second, TS is samples per second, and what I want is samples per bit.
So PS equals to twice NB into TB.
B into TB.
NB into TB.
NB into TB.
Oh, sorry. TO is equal to N. Yes.
Okay, we have TS samples per second. TB is bits per second. So just the unit analysis, and B is TS or TB. Excuse me, that's backwards. It's time, not rate. TS is seconds per sample. TB is seconds per bit. So in fact, it's TB over TS. Which kind of makes sense. TS is going to be much smaller than TB. So this has to be a reasonably large integer, say 10 or something. So TB has to be much larger than TS. Okay. So let's define, so basically what we're going to do here is if we see Bj equal to, once again, 0, 1, 1, 0, 1, and so on, we're going to define a transmitted signal, S of k, which is equal to, basically, we're going to replace the 0 with S0k, the 1 with S1 of k, shift it appropriately. The x1, S1 of k, S0 of k, S1 of k, and so on. And since these each have duration of nb samples, they will all fit into slots of length nb. Okay, best way to see how this works is by example.